the right of that? It could be to the left. Yeah.
Somebody shut that door, please. Thank you very much. I have a handout today. We're going to do two stacks. Okay, guys, need to get started. I'm moving a little slow today because I injured my back. If I yell out, don't worry about it. Any questions about lab today? We're doing the, what is it, tin or zinc? Any questions about lab today?
Are you going to provide the syringes for the suction filtration?
Yeah, like the four cotton balls.
You gotta find the syringes.
Yeah, everything is supplied in lab. Syringe, cotton balls. Do we have any cotton balls?
We needed four cotton balls.
I forgot to check. We had some at some point. If not, I'll pick some up. Other questions about the lab today? It is one of the longest procedures. You don't necessarily have to finish everything today, although there's not really a good stopping point.
So you have to.
Go on.
You don't have to, but you should.
One of the most challenging days of the 8-week sequence is today, okay guys? You need to work very efficiently. It can certainly be done in the allotted time. Monday and Wednesday lab worked pretty good. Tuesday lab last week finished about 45 minutes later than the other two labs. Okay, Frito-Craft's acylation. Acylation, an acyl group, ketone group, typically called a acyl group. Using an acid chloride, also known as an acyl chloride. Mechanism is very similar to other. The halogen is going to complex with a Lewis acid. And so we get this here, yeah. At this point, this chlorine will just leave. And what does that give? It gives the R-carbonyl carbocation. It looks funny, but we've seen it before. Plus AlCl4 minus. We should probably draw that out so we can have the Cl bond later on. What is this here? Acylium ion. We see that in mass spec. Acylium ion. It's resonance stabilized. Electrons down. We can show resonance structure. I'll draw in the carbon. Triple bond to O, one lone pair left. This carbon is sp, it's linear. It's sp linear right there, but I didn't draw it linear. I drew it just like the original. Once it leaves, that becomes linear. It's sp linear. Seen here. Two resonance structures. This is a major resonance structure, right? More bonds, even though charges on oxygen. And we saw this in mass spec, right? This is called the acylium ion. Right? Hopefully it looks familiar. That's what's formed in this reaction mechanism by that mechanism there. Then the benzene ring will attack the acylium ion. Now I can attack right there and that's it. You can always work with any resonance structure. Instead of attacking right there, how about if we attack electrons down, they break away, attack this carbon, and these move over. We do have dipole here. We attack and push electrons back. What does that give? It gives the same thing as if it had just tacked right here. Now bonded to the, we just made that bond, there's an H there. And we're off to our good old mechanism. Sigma complex, resonance stabilized. This is where I should have drawn out the bonds here. We have one AlCl3 minus. Then these electrons can come here, and these electrons can move there. And that gives us our product, right? Plus HCl. Plus we reformed our catalyst, AlCl3. But just like the Friedel-Crafts alkylation, it was a Friedel-Crafts alkylation. This is an acylation, because we put an acyl group on, not just a plain alkyl. There was a couple of problems with alkylation last time. One of them was rearrangement of carbocation. Not a problem unless you want it, unless you don't want it to. This will not rearrange. Why? Because it's resonance stabilized. So your acylium ion doesn't rearrange. So you don't have that problem here. Also, what was another problem with the direct alkylation? Friedel-Crafts alkylation. Polyalkylation. Are we going to have trouble with polyalkylation here? Which is more reactive towards EAS, the starting material or the product? Product has a ketone group. Is that an activator or deactivator?
Deactivator.
Deactivator. Product is less reactive. In fact, can you do Friedel-Crafts with a deactivating group?
No.
You can't even do it. Product is not going to react again. So you're not going to have, you don't have the problem of rearrangements, and you don't have the problem of polyalkylation. There's no such thing as polyacylation in this mechanism. The acylation is thus a much better reaction. And that's shown below. So, no polyacylation. If you look back on the previous page, we showed compound A. What was the yield in the previous on the previous page? Compound A. 35. What was the other product?
65.
How did the other product form?
Rearrangement.
Rearrangement. You're not going to get rearrangements here. This is a much better route to compound A. But it's a two-step route. And what you can do is, compound A requires a 4-carbon chain. Making it directly by Friedel-Crafts alkylation, it's going to be a low yield because of rearrangements. But you can do a two-step route. You can first acylate with the 4 carbons. That would be in a carbonyl. Good yield of that. Then, new chemistry. You can remove the oxygen. You can reduce this carbon to the CH2. So we're replacing the oxygen with 2 H's. It's a reduction. That can be done very routinely. Before we talk about how, we thus say we have a two-step route to compound A now. And the two-step route is highly preferred if you want a good yield of A. If you do it directly, like on the previous page, it's going to be your minor product. So we acylate, then reduce. That is typically always preferred over a direct alkylation. Now, sometimes when the direct alkylation can work, sometimes there's some practical things going on. On paper, the two-step route is better. How do you do the reduction? Three different ways. First off, our good old hydrogenation. Hydrogen with like palladium carbon or nickel or something will do this reaction. We'll do the deoxygenation here. And just like all hydrogen reactions, we're not going to be looking at a mechanism. But remember, you can also reduce nitro to the amino. Look at what we're doing there. We're removing the oxygens, replacing with H's. Removing the oxygen, replacing with H's. Again, we're not looking at mechanism. Now that hydrogenation typically only works well when it's benzylic, when it's next to the aromatic ring. A classical textbook way, and this should be in any textbook, Clemmensen reduction. This is the second way to do it. It's a dissolving metal reduction using zinc HCl. But typically it needs a little mercury with the zinc to sort of activate the zinc, and that's called a mercury amalgam. Clemmensen reduction is a very classical textbook way to accomplish this reaction here. It's a metal reduction, like you're doing in lab this week. We're not going to be looking at a mechanism for that. It's probably a radical mechanism. It's got a name though, a scientist name. Usually when it has a scientist name, you should know those. Third way, Wolff-Kishner reduction. This has two chemist names. I think Wolff should be two F's. I have to check on that. Wolff-Kishner uses hydrazine and hydroxide, and probably heat. We will not look at a mechanism for this today. We will look at this mechanism during test 4 chemistry. Test 4 chemistry is when we cover the chemistry of aldehyde ketones. This is a ketone reaction. But right now we're really not looking specifically at ketone chemistry. So we're not ready to look at it. But we will look at this mechanism during test 3. It will be very classical. Okay? For now, you have 3 reactions. Your choice of accomplishing this part B of the 2-step reaction. What we call a Friedel-Crafts acylation followed by reduction. Miscellaneous comment. A lot of times students want to try to make aldehydes using the acylation. Using this here, where R is H. I haven't defined what R is. Where's our mechanism? It must be up top. Here, pull it down. What can R be? Well, it can't be H, because that compound is not stable. Although I'll show you a tricky way to do that. R typically is not H. R typically means a carbon group. Well, the R can be just about anything. I reckon it can even be SP, but that's just kind of rare. Just about any carbon group is fine, but it can't be H because that's not stable. There is a tricky way to produce this in situ, which means in the reaction. Carbon monoxide and HCl will produce this. And so these combined with that, you can do this reaction. And that's called, I believe, a Goderman-Koch reaction. I haven't really seen it written recently. I think it's Goderman-Koch, maybe it's K-O-C-H. If you look it up on the wiki, you'll probably get a hit. But if you understand that those produce this, and then you do your old mechanism, and R is equaling H essentially then. So that would be a way to get an aldehyde directly on the ring. Questions about that page? So the acylation tends to be a much better reaction. Okay, see if we can predict the products here. Product for the first one. And then the rest are also Friedel-Crafts reactions, either alkylations or acylations. Somebody have the first one?
Plus ortho.
Which ring is reacting in the EAS? You've got two rings, but which one is reacting?
The first one, because it has a cool.
This is going to make your acylium ion, and this attacks the acylium ion. I mean, this ring has a deactivator. It does not even do Friedel-Crafts acylation. This is the ring reacting. What type of director does this ring have on it? Ortho-para. I did a para reaction to add the acyl group. I could have also did ortho. I'll just show it like that. Two products theoretically as two major products. Question?
Is ortho sterically hindered?
Yes, ortho does tend to be sterically hindered, although if you're doing bromination or something, it's okay. I will say this, Friedel-Crafts does tend to prefer para, but still we would say ortho, para are both going to be major products. If you were asked to decide between ortho and para, then you would probably say para is preferred. Okay, how about this guy down here? It says think intramolecular. Just this aluminum, what are we going to envision here?
Two rings.
Complex, ionization, acylium, what can attack it?
The benzene.
This ring, you're going to have an internal, okay? You show product there. What type of director is on this ring? sp3 carbon,
Group 2.
ortho-para director. Ortho position. Para is not going to be able to attack. It's going to be ortho. What size ring are we making? We just made that bond there. We now have we made the 5-membered ring. The benzene ring is now bonded to the carbonyl or acyl group. If you don't see it, you should work through your mechanism. It's very straightforward. This position is attacking the acylium ion. The para position can't attack. It's over here. It's not going to be able to attack. So just one product right there, yeah? So that would be an intramolecular Friedel-Crafts acylation reaction. How about below? We have phenol, T-butanol, sulfuric acid. What type of chemistry do you envision going on here, mechanistically?
You hydrate the OH oils and then.
We're starting more and more, we're starting to, okay, you've got multiple reactions that you can envision. I got an aromatic ring with an activating group. That means we need some type of electrophile. What type of electrophile we got there? H+? Well, that's not going to do us any good. What type of chemistry can we envision?
Hydrate the TD.
Making
Hydrate the T-butyl.
What carbocation?
The T-butyl, yeah.
Protonate, ionize? Yeah, tertiary carbocation. I assume you can protonate, right? Ionize to give a very nice T-butyl cation, right? Can this attack T-butyl cation? Sure. What type of director do we have? Orthopara. So I'm going to show maybe a para reaction, okay? Go through your mechanism, attack. Last step is remove the hydrogen, restore the aromaticity. Okay, mechanism, you should. I showed para, you could also maybe do ortho. Now, what's possible? Is this going to rearrange?
No.
No, I ain't going to rearrange. But what could happen here? What's some possible concerns about this, getting this in good yield?
Okay, yeah, ortho. On that.
Once you add this on, now you've got not only a strong activator, now you've added a mild activator. This is more reactive than that. So it can start reacting again. Polyalkylation, right? If it added again, where would it add?
Ortho.
Still there. Yeah. And actually, in one of the, occasionally we do a lab where you react phenol with that, and you use an excess of that, and you end up with all three positions alkylated. Because it's actually hard just to put one group on. Putting all three on, you get a better yield. Putting it here and here is not helped by this group, so it doesn't go there. Particularly, it now becomes very sterically congested. But making that product there is pretty easy just by using 3 equivalents of this. And some of the organic professors do this reaction in the lab. How about this down here? What type of chemistry can you imagine around here? That's just organic 1 chemistry, right? H plus. Get this cation. The ring can attack here just like this. And so you can get that bond made to there. Of course, you can also say plus ortho, or then you worry about, well, is it going to do a dialkylation or a trialkylation? In terms of just putting one group, the main thing, do you understand the chemistry? In all these cases, we're making a carbocation, right? Make a carbocation from an alcohol, make a carbocation from an alkene. Okay?
For the question, the previous question with the alcohol, if it was like predicted product, would we go with the polyalkylation answer, or do we show orthopara and the polyalkylation?
I'd probably just want you to do just mono and say, like, show both para and ortho. But be aware that this could happen. Okay, so there's some carbocation chemistry.
So we wouldn't expect the same level of polyalkylation here because of those sterics, right?
You could. You could. We're just not defining it that well because you could get mono, di, tri. If you used excess, the question becomes, well, if you can get 3 2-butyls on there, then you ought to be able to get 3 of these other groups on there. Okay. Some examples. see what we have here. This is a synthesis of Tazarac, which is used as an acne medication prescription. Here's a synthesis of it. The first compound is a alkylation, really a Williams and ether synthesis of the sulfur. The base takes the H, and then the anion does the alkylation, SN2. So that's how we get to that point, right? Look at the next reaction there. What's going on in the next reaction? Don't worry about P2O5. Main thing here for us is phosphoric acid. Can you envision what's going on there? What's the first step of the mechanism, most likely? Got an alkene, and we end up with making a bond to the aromatic. Alkenes reacting with the H+. Just like organic 1. If this reacts with H+, where are we going to leave cation? Left or right? On the right. It'd be a tertiary cation. And then guess what attacks the tertiary cation? The ring at that position. What type of director is the sulfur? Orthopara. So the ortho attacking makes sense from the directing. Okay? That's a good old classical mechanism. That's how we get that bond made right there. Make that ring. But look what they're doing next. What's the next step? That's an acylation. They're not using aluminum trichloride, they're using tin tetrachloride, which is another example of Lewis acid. It's not quite as strong. Lewis acid, this complexes with the tin first. Okay, from there it's the same old mechanism. What type of directors do we have? Which one's going to win out? The sp3 carbon or the sulfur or the lone pair?
Sulfur.
Yeah, so it's your director. Orthopara, where does the new group go? Para to the sulfur. Possibly they got some that went here, and maybe they got a minor amount of that and purified it out or something. But it makes sense that the new group went para to the sulfur. From there, that chemistry, you don't know that, but they're getting an alkyne. Nothing. I think the only thing left that we would know would be right here. This alkyne, they say then, that's important, or they could have said 1, 2. Indutylithium, strong base. What does it do to this compound? Deprotonates the alkyne hydrogen, and indutylithium. We know that chemistry, right? Then when they get the anion here, it then adds to the zinc. You can also kick off a chlorine. They're making this bond to the zinc. That's an organometallic, similar to like a Grignard. And from there, they're doing a palladium catalyzed coupling. We don't know that chemistry, but palladium chemistry won Nobel Prize in 2010. There's also a palladium reaction in the 8-week lab called the Suzuki reaction. Suzuki was when you use boron. When you use zinc, it's called a Negishi reaction, N-E-G-I-S-H-I, something like that. Negishi was a chemist at Purdue. Negishi shared in the Nobel Prize 2010 with Suzuki and with Heck, H-E-C-K. On the back is a synthesis of, Vioxx used to be $1 million drug, really probably $1 billion, about 15 years ago, but then it had heart side effects and they had to pull it. Like a COX-2 inhibitor. See this molecule here? What's it got? About 15 carbons, a couple of oxygens and sulfur. You're looking at $1 billion drug right there. Fortunately, they had to pull it because of heart side effects. But here's a synthesis of it. What's the first step? Assuming you can buy the compound with the SH, Friedel-Crafts. Just showing pair product. A couple of by-the-ways. Rest of the way, we'll see that reaction and this reaction during test 4. I'll actually give you the same handout when we get over there. This one we could have looked at in organic 1. This is nothing more than, once they get the bromine on, what are they doing? This nucleophile replaces the bromine and they're making that bond right there. There's your nucleophile. Used to be a bromine there, right? So that's just a good old SN2. When we get through everything we should have covered, we typically don't cover sulfur oxidation, but you can oxidize the sulfur. In the end, Frito Crafts is pretty versatile, pretty useful chemistry. Questions about Frito Crafts? That handout? Did everybody get a orange or coral colored, whatever color that is? Everybody get one today? I don't know if I was going to show this or not, but let me show it while we're moving over. Organic syntheses. You look this up online, top left, organic syntheses. Procedures have been published like this for going on 100 years. You can find the exact procedures. Of course, not everything is here, but common things. For example, here's a synthesis of para-iodoaniline, starting from aniline, using iodine. The way we showed it in class, you had to use iodine plus what?
Oxygen.
Plus an oxidant? Yes. They're not using an oxidant here. Why is there no oxidant required? Sodium bicarbonate is not an oxidant. What's the purpose of that? No oxidant is required because, how reactive is this?
Pretty reactive. It's pretty good point.
Yeah,
Is this an activating group? This is a pretty reactive ring because we have a strong activator. Because it's a strong activator, you really don't need an oxidant. Okay? Actually, with bromine, what do you have to use to brominate? Lewis acid. Okay? That's textbook. Lewis textbook. If your ring is very activated, like a strong activator, typically you don't need the Lewis acid sometimes, or you don't need the oxidant. That's the only thing I'm showing you here. Okay? So if you ever don't see it, say, where's the Lewis acid? Well, check out your ring. Is it highly activated for some reason? All right? What's the purpose of the sodium bicarbonate? Well, if you don't have any base here, what is the line reaction produces this plus what? It's going to produce HI. Well, HI is a strong acid. What's that going to do to your starting material? It's an amine. Well, it's conjugated, it still will do it. It'll protonate the starting material. And if you protonate the starting material, what happens to your activator? It ain't an activator anymore. It's also not an ortho-pair director. You need some base to keep this from protonating your starting material. So include a little base. You can look at the reaction. I was actually trying to find a reaction where they talked about how they separate the para from the ortho. I couldn't find one. I only looked for a little bit. That's what I was really looking for, to show you how they had to maybe deal with separating the two major isomers. But there are a couple of things here. And another reason, you don't have the handout, but they recrystallize the product. What do they recrystallize it from? I thought that was funny. They recrystallized it from gasoline. See, what year was this?
1943.
It's back in 1943 when they didn't maybe have good access to like hexane or something. But they had the gas pump down on the corner. And they actually, the hot gasoline solution, okay, they
That's terrifying.
okay.
Yeah, let's heat up some.
They also give a note. You know, notes are very important. Can y'all read that?
Yeah. Hair dryer.
Commercial hair dryer to dry their products. Okay. there was a note about the gasoline. The gasoline used was a fractionated product. They actually distilled their gasoline before using it. But the note says that ordinary gasoline may be used, but it has a disadvantage of higher boiling hydrocarbons that are removed slowly from the product. So they recommend distilling their gasoline first. Okay? This is okay, the coral colored sheet. Now we're moving on to our next chemistry. We covered EAS. Remember early on there were 3 mechanisms. We're moving on to mechanism number 2. I'm sorry.
I didn't get a sheet.
No, are there any more coral ones around in the back? Okay, early on I showed you the 3 mechanisms. Please make sure you look back at the comments made there. That is, EAS, we typically replacing an H. So the H is leaving, but H ain't typically called our leaving group. When we think leaving groups, we do typically think back at the SN1, SN2 chemistry, okay? Although ES is different from that. I agree that when you hear leaving group, you think more of like a chloride anion or bromide anion. Those are your traditional leaving groups. But you've got to be careful about what mechanism you're talking about. Certainly in EAS, we just, an H left, which is, it's actually leaving as H+. Okay, in our other mechanisms, we're going to see more of a traditional leaving group. Is that better?
Yes. Yeah.
Okay. That's warm up. You can look at that. What's the name of this mechanism? Well, leaving groups on the aromatic screen. Maybe we should look at the warm up because it is illustrative. First reaction, what's going on there? Looks like the ethoxy, it looks like the nucleophile, the O- is replacing the chlorine. This looks more like a traditional substitution reaction. Okay? All right. Down here, no reaction. Why? Well, once we know, of course there should be no reaction down there. Okay? So, right now I'm calling it substitution of a leaving group by a nucleophile. We're going to have a ring with a more traditional leaving group. We'll define leaving groups as we go further. In EAS, the ring reacted with an electrophile. Electrophilic aromatic substitution. The E stands for what the ring is reacting with. Here the ring is reacting with a nucleophile. And later on we're going to call it NAS. Nucleophilic aromatic substitution. But right now I'm just calling it substitution of leaving group by a nucleophile. There's a generic reaction. Mechanism. First off, it ain't SN2. Because SN2 only occurs on one type of carbon. Tetrahedral. The leaving group ain't on a tetrahedral carbon. It ain't SN2. It ain't SN1 because you would make a carbocation, and that carbocation is worse than a primary carbocation. You're not going to do that. So it's not either SN1 or SN2. Those are mechanisms that only occur when the leaving group's on a tetrahedral carbon. Well, it ain't EAS because the ring ain't reacting with an electrophile. It's reacting with a nucleophile here. So it must be a new mechanism. Indeed it is. And we have 2 choices. It's either NAS or benzyne. Now it's actually NAS here, which stands for nucleophilic aromatic substitution. Let's look at the mechanism below. Okay, how can we do this? Well, What's our reagent? Electrophile or nucleophile? Let's get rid of that. Okay. Nucleophile, right? Okay. Hopefully you know that at this point. Nucleophile. Obviously, the nucleophile's got to replace the chlorine. We've got product shown. And we're showing that it's going to produce chloride. Sodium can sit with that, we can make sodium chloride. Okay? So, what do you want to do first? Do you want to have this come in and kick that off all at the same time?
Nice. That'd be nice.
Well, that'd be SN2, and we said that that ain't the mechanism.
You can't take the CO off.
Do you want to have this leave and make a cation?
Cancel that.
That would be like SN1. We said that ain't the mechanism.
What if the NA takes That's what I'm saying.
All right, pretend these bonds are drawn in nice and precise. Do we have any reactivity? Why would this react with this? We have a dipole here. We have dipole. There's some partial positive here. This attacks, okay, pretend like this is drawn in better. We can even draw it in better. These electrons move here. Because look, if a nucleophile attacks here, what's going to break first? Pi bond to carbon or sigma bond to chlorine? Pi bond to carbon. Why? Have we heard that before? Yes. Pi bond's going to break. These electrons move here. What does that give? We got both a chlorine and a nucleophile bonded there. The electrons moved here as a lone pair. That's a minus, and nothing happened here. There's an H there, right? We didn't get rid of that H, that's why it's a minus. Now, does this look like an SN2? No. SN1? No. It's something new. What did we do here? We did a nucleophilic addition. No, there's no stereochemistry here. You mean here?
Yes.
Actually, I mean, I've never even considered that. But yeah, that is a chiral carbon, and that is stereochemistry, but it's not going to matter over there. It's an interesting question. I've never considered that. But yeah, that is chiral. Okay. Now what can we do? Come again?
With the lone pair, go back in the ring and kick the chlorine out.
Have you ever seen anything like that?
Yeah.
When we were dealing with first week, we saw some stuff like that. Addition followed by what?
Elimination.
Elimination. Now we kick off. Which one's a better leaving group?
CO.
Yes, we kick that off. What does that give? It gives that. Addition followed by elimination. Just like what we saw with like the thionyl-chloride type stuff, tosyl chloride. Okay? And I remember we said, here we're going to break the pi bond. Okay, does that look like SN2? No. Does it look like SN1? No. It's called a nucleophilic aromatic substitution. It also goes by the name of what? Additional elimination, which is more descriptive. Okay? Now, come back here. Does this have any stability? We made a carbanion here. Does it have any stability?
Yeah, resonance state.
Yes. Electrons here, electrons out. Boom. Minus, boom. And we can draw other resonance structure. One more. Electrons in, electrons out. With the anion here, boom, boom. Nucleophilic addition to give a resonance stabilized carbanion. followed by elimination. Question?
Does that mean the elimination is gonna be the rate determining?
Well, that's an interesting question. There's a question in the workbook that sort of gets at that. Rate determining step is typically here unless something odd is going on. Because if you plotted this, and maybe we should, we go from, I'll let you do that. We have start, okay? This would be A, B, and C. Where's B? C is pretty much hard to say which is different. They're both aromatic systems. But where's the intermediate B? It'll be up here, right? It's a carbanion, much higher energy. Also, it's not aromatic, because that's a tetrahedral carbon. It's no longer aromatic. It's a carbanion, much higher in energy. Forming that's going to be your rate determining step, yeah? And then here, you don't need much energy to fall downhill. Two-step mechanism. Here, okay, here's the kicker. This reaction doesn't work.
No reaction.
This reaction doesn't work as drawn. Because this carbanion is too unstable to make, even though it's resonance stabilized. Well, first off, we know it doesn't work because if you go to the lab and mix these with mild heat, you don't get a reaction. So then we have to say why. Well, the reason has to be because the rate determining step must be too difficult. Obviously, right? Well, if the rate determining step is too difficult, that implies that this is too high in energy. So all that's just implied from what we see. Even though it's resonance stabilized, it's too high in energy. Apparently so. What does it say below? Requirement. NAS only works if you can stabilize this, lower it down. It's already stabilized by resonance. I don't know. You need more resonance. How can we get more resonance? Only by adding a group. For example, if we add a ketone here, just add a methyl ketone to the ortho position, ortho to where the chlorine was. If that is present, if this is the starting material instead, what is that? 2-chloroacetophenone? Orthochloroacetophenone? That will work. Why? Why does it give you, right here, an additional resonance structure? Everybody added the ketone? Now with your ketone added, can you draw an additional resonance structure? Now we can move the electrons in here and move these here. Presence of that group gives you an additional resonance structure that looks like what? Looks like that. Not only is it an additional resonance structure, where are we now putting the anion? Carbon, carbon, carbon. Now with this group we're able to put it on oxygen, and that is so much better. Now the reaction works. And we have to then assume that this is why it works, because we're able to put the minus where? On a heteroatom. Putting the minus on heteroatom apparently lowers your energy of your intermediate enough to make it work at reasonable temperatures. Or really to make it work at any temperature. If you have too high heat, it'll actually start going by a different mechanism, and that'll be the benzyne mechanism. Here's the requirement. NAS only works if you have a strong electron withdrawing group, ortho or para, to the leaving group. I put in ortho. Note, the group has to be connected to wherever the anion fell. It fell ortho, falls para. We could have put the group here and moved it into the group para. Ortho. See, both of these are ortho to the chlorine para. The strong electron withdrawing group, which typically is going to have a pi bond to a heteroatom, such as a ketone or nitro or others, needs to be ortho-apparent to the leaving group, like I added. Now it will work. And you end up with that there. That will work. Rate determining step, we already labeled it. Leaving groups. Look at your mechanism. Does the leaving group leave in the rate determining step?
No.
No. That is unique. Think SN2. Does the leaving group leave in the rate determining step of an SN2?
Yes.
It does, yes. SN1, does it leave in the rate determining step?
Yes.
Yes, it does. NAS, it does not. What's the consequences? SN1, SN2 have very strict leaving group requirements. Halogens or tosylate, right? In this mechanism, just about anything that can hold a negative charge will be able to leave. Can oxygen hold a negative charge? If you've ever seen it with a negative charge, it can leave here. Have you ever seen oxygen with a negative charge?
Yes.
All the time, hydroxide. Well, guess what? Oxygen has no trouble leaving here. You can even have carbons leave if the carbon is stabilized somehow. It's not going to leave as like an alkyl, but we'll see lots more leaving groups here because the leaving group leaves in the fast step, and so you don't have those restrictions like SN1, SN2. All right, let's go back on the front. Why does the first reaction work? Well, the leaving group has what ortho-apparent? If you do your mechanism, you can draw resonance structures into the nitro group. Why does this one not work? Here's your traditional leaving group. Does it have a strong withdrawing group ortho-apparent?
No.
No, that's not a strong withdrawing group. You're not going to be able to do any resonance with that group. That's why it doesn't work. Please look ahead in this. Included in this handout is our third mechanism, the Benzyme mechanism. Okay, guys, see some of you this afternoon upstairs.